So yeah, so then I guess AES Workshop, DSP Day 3. Let's go. All right, so quick recap from last week, I guess, and stop me if you need me to go over anything. So we have the difference equation that we found, which was the time domain version, and then leading into a transfer function. And we kind of learned how to take a transfer function and the difference equation, whichever one, and convert it into these kind of representations, either a pole zero representation or the frequency response curve, and then also just getting the unit sample response from the impulse input. So that's frequency response, C-plane, poles and zeros. Yeah, so we basically can analyze transfer functions, analyze difference equations, because they're basically the same thing. And then we can make high, low, band, all those kind of filters, I think. Not really sure. So we kind of got into it, but I don't know if like it's a comfortable topic yet. So I guess we'll start off with just like a review of that, and just kind of, not really a review, but I guess kind of like looking at the applications. So yeah. And then there's also this problem that we don't actually know how to analyze a signal. We know how to analyze these filters given the AK, BK, the coefficients, the difference equation, whatever it is. But if you're handed just some input signal, like from a microphone or something like that, we still don't really have any good way to analyze that. We can apply a filter to it, but we can't even really look at the output. So today's goals basically is going to be review basic filter design, add some rules that we didn't cover last week, just kind of had to be glossed over last week, but they are important. And then we should be able to make from that high pass, low pass, band pass, and band stop, and there are some others. And then the second thing that we'll do is we'll develop a signal analysis tool. So the Discrete Fourier Transform, the DFT. It turns out we don't actually need to build this function. It already exists in MATLAB, thankfully. But it's pretty useful to understand at least kind of what it's doing on an intuitive level. So I'm going to try and lay that down. I've looked at it quite a few times because there's multiple classes that look at this, and then you spend multiple hours banging your head against the wall doing homework doing it. And it still sometimes seems confusing to me. So if it seems confusing after this, you know, it's just a first exposure, I guess, is a good way to think about it. So we'll see how far we get, I guess. So starting with filter design, I guess, we have that frequency lives kind of on this Z-plane unit circle. So down here, I guess. So it starts with Z equals 1, and that just comes from the fact that there's that at F equals 0, you have Z equals e to the J2 pi F. And so that just kind of starts over here. And then at 0.5, it evaluates to -1. And so it kind of rotates around. And then after it rotates to here, you start repeating yourself, and then eventually you'll get back to where you started. Haley, if you're coming from 228, that's probably different than you're used to, because in continuous time, they have it on the j omega axis. So in this, just think about it as the j omega axis is wrapping around and eventually goes back. But the j omega axis has kind of been converted to the unit circle.
Oh, okay. Thanks for explaining that.
Yeah, so this is your lowest frequency, and then this is the highest frequency that you'll have. And then you start getting back to, it's a thing about digital, and I can explain it more later if you need, but the basic idea is that that's where your frequency kind of lives. So if we're looking at this pole zero map, then you have the zeros pull the frequency response down. So if you see like there's a 0 here, and that pulls it down, and then same thing with this 0 over here, pulls it down right before you hit 0.5. And then poles will pull the frequency response up. If you don't set them anywhere and you just put them at the origin, then they just exist at the origin. But you can move these poles around as well, and they'll kind of boost. If you're at some frequency that's nearby to a pole, it'll kind of be lifted up. That'll also have some implications actually with regards to where the poles can go, because you can go to 0, but poles technically, if you're right on top of a pole, they're like infinite gain. So there are some limitations because of that. So other rules, complex zeros and poles have to have conjugate symmetry. This is just because if you have, let's say one of your poles is like a plus JB, like some complex kind of thing, you'd want your other, zero. You'd want your other zero to also have complex conjugate symmetry so that when you FOIL them out, the complex parts will cancel. If you don't do that, your difference equation will basically end up being, it'll have complex terms in it. And so you'll be evaluating, it's not physically realizable, first of all, but secondly, your computer will do faster math if it doesn't have to handle imaginary numbers as well. So, so the complex conjugate, you can see what that means just here. If you have it on the top, it's got to be on the bottom. Same here. If it's on the real line, obviously you're fine. I actually went ahead, the pole zeros function that we have, I modified that, and so that's in the drive, but I modified it so that you only have to put in one of these poles or zeros and it will automatically mirror it to the other side as well. So it just, because there's never really a situation where you'll just have one and not the other. It kind of makes sense to do that. The final thing is that all poles have to be inside the unit circle. And so that's for stability. If these poles here are lifting up and shooting the gain up to infinite, essentially, then they can't really ever be on this unit circle, because if that's where your frequency is actually being evaluated, you're going to be like multiplying or convolving the signal by an infinite quantity. So that'll make your whole system unstable. So that's here, you have the A plus JB, plus or minus, or if it's in E to the J theta, you just have plus minus as well. And then pole stability, the poles just have to always be less than 1. Can't be equal to 1, can't be greater than 1, just less than. So any questions on that? Very good.
Quick question. So for conjugate symmetry, is there ever a condition where you could have a zero or pole only on one side of the real axis, even if it's not physically realizable? Like, is it possible to design a circuit that could achieve that? You
can. I don't personally know of any applications why you would want to do that. There might be some mathematical kind of justification or reason for wanting to do that. Mm-hmm. But typically, I mean, at least for like audio uses or any like real world engineering kind of thing, as far as I'm aware, it's really just you'd want them to be like this. Because if you're not in digital systems, you can't have complex terms because you can't put that into your circuit. Yeah. If you're in the digital world, you can have complex terms, but then it slows down your computation. So I don't know of a reason why, like when it would be useful to do that. There might be, I just don't know what it is. So yeah, that's a good question, but I honestly don't know the answer to that. Okay, cool. So I don't know, I figured we could kind of go through, I'm gonna like get out of this PowerPoint for a second, just with filter design. So implementing basically a low pass, a high pass, a band pass, band stop, and finally these other two filters, one that repeats the input signal one sample later, and a filter that recursively kind of plays the output from one sample before. And so to do that, I guess the easiest way to do that, let's see. Also, I found out why, I'm gonna collect my thoughts here. I found out why this wasn't running last time. It was just like a path issue of like MATLAB was seeing like duplicate files. So I'm just gonna use this. So if we go back to, I guess, picturing, where was it? So we have our unit circle. So if we have some incoming signal and we want to apply a filter to it, if we wanted to make a low pass filter, just curious, does anyone have any intuitions about what you would want your zeros and poles to be on this plane? That's a no.
No, at least not initially.
All right. So basically, once I explain it, it should start becoming a little bit clearer. But yeah, these are kind of weird concepts to actually apply. So you have your frequency starting here at f equals 0, like the lowest frequency you're going to have, and then it kind of increases up to the highest frequency that you'll have in your digital system at 0.5. So if you wanted to make something that was, so first of all, if you don't have any poles or zeros, your transfer function, which is just, it's just going to be zeros on top and poles on the bottom. And remember, it's not exactly multiplying, but for this, it doesn't hurt to think of it like that. But convolution, you're basically just taking whatever point you're at, and you're kind of going to multiply it by the 0 and then divide it by the pole. And so if you have no poles or zeros, it's just going to be 1/1. And so it's just unity gain across the entire frequency spectrum. So if you put a 0, you're going to pull that frequency response down. And then if you put a pole, you're going to kind of pull it up anywhere that's nearby. So this, it can kind of be visualized as like this 3D surface, and you're like rotating around on it. And so wherever there's a pull, it's almost like if you've seen those visualizations of like a black hole or something, like, you know, they like bend space-time or whatever. It's kind of like that. And then same thing with a pull. If it pushes up, that point goes to infinity. And so the surrounding points are kind of pulled up by it. So if you wanted a low pass filter, let's say, you would want this low frequency side over here to be at unity gain. And so you don't really want to disturb that. And so you'd want this side, though, to go down to 0. So you would just basically place one of your zeros here. And so then when you start, you'd be at unity gain. And then as you get closer and closer to that point, you're going to start kind of being pulled down. And so that'll pull you to 0. So if we go into MATLAB, and this is just the function, the show filter response is PZ. It's in the drive. So you can do this pretty easily. So we'll put in a 0 at -1, and we'll just clear this out. Put the pole at 0. The gain is just, you mess around with that after. But if we run this, so that's kind of our frequency response. And you can see that we would actually need to modify that gain term, because at 0 frequency, we're hitting about 2. And if you'd want it to be like a unity gain low pass, you'd want that to be 1. So you'd just kind of mess around with the K, but that's the basic idea, is that you're starting here, you put a 0 here. Interestingly, however many zeros or poles you have, you're going to have the same number of the other one. So if you have, like you saw that I put in like one over here, it'll just kind of put one at the origin. Like I put it in, but if I put another 0 in somewhere else, it'll actually make a second pull to kind of match that. And it'll just automatically, the math kind of just works out that those will be placed evenly.
Are the poles always in the center?
No, so the poles you can move, but in this case, just for like a low pass filter, you don't really have any reason to want to pull up more at any point. So it makes sense to put the pulling up to infinity at the origin so that all the points equidistant from that around the unit circle are kind of pulled up the same amount. Does that make sense?
Yeah.
Cool. So yeah, so then I guess if you wanted to make high pass, oh, that's what I should have pulled up earlier. It's just this. So yeah, if we wanted to make a high pass, then the idea is we don't want to disturb the high frequencies. We'd want to basically get rid of all the low frequencies. So we can move the 0 to the other side. And now when you do that, it looks like this. This is just the unit sample response. It's interesting. I'm not really going to focus on it right now. But yeah, so that's two of the more nice ones. But now that we kind of have that as like an intuition, I want to see, what was it? Whoa, band pass filter. So if I'm trying to pass certain frequencies, I guess it's worth asking, where should I place what?
Would you place a pole on the frequency that you're trying to pass, or would you just place a hole on either side? What's the way that you do that?
Yeah, so that's pretty good. You wouldn't place the pole exactly at the point that you want, because if you do that, you're going to shoot it up to infinity at that point. But you can move these poles around, and let's say we wanted to put it, I guess, like at 0.25, just so that it's halfway around the circle, or halfway around this side of the circle. If we place the pole kind of nearby, then it'll push up everything around that. And did we say we were making band pass or band stop? Band pass? Okay. So yeah, we kind of want it to look like this then. So if you place the pole kind of nearby that point, it should shoot up there. And as long as you put 0s on either side of it, it'll pull down. So yeah, you can move these 0s closer to get like a sharper transition. So here, let's go ahead and do that. So we'll put the 0s, I guess, at 1 and -1. And then we'll put the pole at J. Oh, you can't put it at J. I just finished saying that we can't do that. It's like, why is it so sharp? There we go. So yeah, so this is kind of pushing these points up, and then these 0s are pulling them down. So that's kind of what's going to happen in between. And then you can see if we modify these 0s, we can move them, let's say, to 0.3. And I think this is it. Rather unexpected, actually. Oh no, I guess that makes sense. If you move So yeah, if you move your zeros in, the only problem is that these poles here are going to be pushing everything up. So it's eventually going to actually go back up to trying to get back to unity or whatever. So yeah, I would say if you want, it's a good idea to just like play around with it, try and get like some intuition for it. But yeah, this also leads us, I guess, to the final type of filter, and then there are these two, which I'll kind of just tell you how those work. But yeah, so your final filter, band stop, basically if you wanted to do that, it would kind of be like this, but so we'll put it, we'll stop 0.25. And so if you just do that, it won't really achieve what we want. Oh, run the whole thing. So we just have a 0 here. That's not really going to do what we want because it's just going to, what is it, pull it down. But depending on like how much we want to pull it down, you can also move these poles kind of closer and say like 0.6J. So that'll kind of make it sharper. And you can just think of this pole as being, it's pushing all of these up more that it's closer to. And so the transition between where they're up and where they hit 0 is going to be a little bit steeper. Okay, cool. So yeah, the final two are basically just, if you have a filter that repeats the input signal one sample later, that is equivalent to, let's see, it's actually in here. So if you have some filter that's going to repeat the input sample, well, then that's going to be, you want this x and -1 term. You want it delayed by 1. So that just means that you're going to have a b coefficient. So instead of setting it through poles and zeros, this is more time-based rather than frequency-based. So this is where you would set it, instead of being in the pole 0 domain, we would set it through the AKs and BK coefficients. And so if you're trying to repeat that segment 1 later, you'd want this to be 1 so that you have your original signal. And then you'd also want a 1 on the B1 coefficient so that it's doing 1 times whatever it was 1 sample prior. And then if you want a filter that recursively plays the output from 1 sample before, well, then you just want an A1 term so that your, whatever your output was, you're doing some multiple of that. Interesting note, if your poles are constrained, that your poles can't go outside of the unit circle, then that means that there's a lot of flipping around. That means that these poles here, these terms, can't be greater than 1, right? But if to get back to the difference equation, you had to kind of multiply these to the other side, that actually means that as a consequence, these A terms cannot be bigger than 1. So just kind of rule of thumb, if you're setting A's and B's, these A terms, you can't have a gain that multiplies your output by, you know, something, it can't produce gain on whatever it's outputting, because then you just kind of end up in this feedback loop, right? So yeah, does that make sense, everything? Is there anything that was kind of weird? Okay, cool. So yeah, so that is basic like filter design kind of stuff. So you can do quite a bit actually with just that knowledge, because we already have the filter command. And so if you have your A's and your B's, or however it is that you're getting that transfer function, we have a way to apply it to a signal. So this kind of brings us to the second thing of analyzing the signal. So we can apply the filter. You have this filter, BK, AK, and your input that you want, and that'll give you an output. And MATLAB or Octave or whatever you're using, that will just run that difference equation and kind of brute force the calculation on it. And yes, you can get your output, but you do need to know the filter's transfer function. And it's not very useful for analyzing an incoming signal or just seeing what you output. So there's this note, we can get a transfer function from the impulse response because the impulse response is kind of how we characterized the transfer function of the system initially, is we hit it with an impulse and we see what response it gets. So you can get a transfer function from the impulse response, but if you don't hit it with an impulse response, and let's say you have some other stuff going through it, yeah, you can't really get that transfer function very easily. So anyway, to analyze stuff, we need the DFT, which is the Discrete Fourier Transform. So this comes off the Fourier Transform, which I think is a lot harder actually. The Discrete Fourier Transform at least makes some intuitive sense because you're dealing with discrete values and not integrals of continuous values. So thank God for that. So it's about to get crazy. We'll see if this works. All right, so looking at the DFT, it's basically scanning your input signal, your XN, at these increasing multiples of frequency to see if that frequency exists or if any multiple of that frequency exists in the signal. And so the variable increasing, this is not the exact DFT, but it's pretty close. So the variable of interest here is n. And as it increases, this E term causes rotation, because remember, e to the imaginary, that's just going to be a rotation by that amount. So it causes this clockwise rotation around the unit circle. I'm doing clockwise wrong, but yeah. So at the same time, we're slowly advancing through this signal n. At the same time that we're doing this rotation, we're advancing through indices on this xn. And so the idea is that everywhere that xn is allowed, that it has some non-zero value or some bigger value, we're going to see this rotation vector get magnified in whatever direction it's pointing around the unit circle. And then if xn happens to be small at that point in time, we're going to see this smaller vector, diminished vector. If it's 0, we're not going to see anything in that same direction around the unit circle. So I kind of broke it up so you have this xn, which is this scaling of how much we're going to, scale this rotation. Then the clockwise rotation is this e to the j term. So all of this 2 pi k. So if you do e to the j or I, and then you have 2 pi, it's going to rotate one full rotation around the circle. So this k is basically just like providing a fractional rotation. So it's a fraction of this 2 pi. And so you can set k larger or smaller depending on how quickly you want to rotate around the circle. And then the n is just increasing how many multiples we're kind of ticking around the unit circle. So yeah, the k is going to be small. It's going to be smaller than 0.5 for now. That'll get changed eventually, but yeah, it's a small number. It's fractional. And then yeah, don't worry about xn because we'll just assume it's 1. And we'll set k equal to 0.1, so it'll be 1/10 that we're multiplying this 2 pi by. So start out with this. It's pointing kind of at the e to the 0, right? And so as we go, this is just increasing n. We're going to start kind of rotating this e to the j. So we have n equals 1, n equals 2, n equals 3, n equals 4. And so we're going to keep on getting this rotation until we hit 9. And then once we get back to e to the 10, well, if we have kind of 10 over 10 is this k term, because we've been multiplying by 0.1, then we're going to reach 2 pi. So we have this full rotation around the circle. And so we're back where we started. And so it's just kind of cyclical. Also, just note that it goes up to 1 minus the number that you're kind of dividing by. So we were dividing by 10, it goes up to 9, and then we're back where we started. So then we can change k. So if we make k like 1/6, well then we're doing just pi over 6 is our increment, right? And so we're kind of like rotating faster and we're jumping quicker around this circle. And then if we increase that, we can get more points, right? So this should all be making sense. So now we'll add in x of n. And so we have, you know, let's say 1, 0, 0, 1, 0, 0. So it's cyclical of like an n equals 3. So with this same 1 over 10 kind of term, so every time, the way I've done this is every time that we have a 1 here, there's going to be a purple dot or some colored dot. And then if we don't have anything, it's just not going to have a dot. It's going to be an empty dot. And these purple lines kind of show like where we actually found a 1 versus, because otherwise it's multiplying by 0 and it's the vector doesn't go anywhere, right? So as we're going around, this is rotating, but then we're also iterating through this x of n signal. And so we get them kind of at every multiple of 3. And so we'll hit 8, and there's 9, and we hit 10, we already had a dot there. And we start getting, you know, now at 12, right? What is going on? Oh, okay, I can't color properly. But anyway, yeah, so that should be logical, but it's not the way the slides are going, but you should be able to just fix that in your brain. So anyway, what has started happening though is I started kind of building up this like plot of like where the hits are actually landing, where the tip of this vector is actually landing for each n. And so you'll notice that as we start going, because these multiples of 3 don't really overlap with this 10, we're getting these multiples at like all these different locations. And so we wind up with this distribution of points kind of across all points on the real axis, right? And so what's interesting though is if we change this k, we can get different distributions. So like if we change it, now it's a multiple of 3, but it's every 6, right? We get them at the positive and at the negative side. But then again, if we change it to like 1 over 20, it's kind of distributed everywhere. And if we change it to 1 over 40, it's just still distributed everywhere. So the conclusion is basically that some values of k will give you these frequent hits that are in the same place. And if you have one place where it's really concentrated, that's going to contain more of that particular frequency. It means that your x of n contains more of that frequency because it's happening at the same point every single time. So yeah, when more hits skew to one side, then you can think of the center of mass. It's the average weight of like those hits, and it'll give a non-zero amplitude. So I stole this from 3 Blue 1 Brown. If you don't know that YouTube channel, go check it out. It's really awesome. But he kind of talks about this for Fourier transforms, this x coordinate being your center of mass of all of these dots. And so there's certain points at which you're going to have a peak that happens. And so you can see when you put it at 3 as your n, well, I mean, you're basically just going around, I don't know how this is working actually. Oh, because I didn't modify the whole picture. Anyway, you go 0, 1, 2, 3, right? And then you keep on winding up back at the same point. So all your dots are going to be concentrated. And so if you look at where what the weighting is of this over frequency, over this n value as you change it, you're going to see that some of these values cause more weighting than others. And so in this case, we get a positive value of the weight. It's actually, it evaluates to 0 here. This also evaluates to 0, 0. So most of these terms will evaluate to 0. And then at the points where the frequency is in that, you'll get some non-zero term, and that's your peak. So the only change we need to make to the DFT, we were using K as like a fractional constant. And so that modifies like how quickly we're rotating around the circle. So we can change it to K over capital N. And so now the advantage of doing that is that we can control this constant fraction speed of rotation by using integers for K. So we can plug in a value 0, 1, 2, whatever. And we can go all the way up to n minus 1. So if you do that, you're going to be almost going a full rotation every single time. And so, yeah, so we can see kind of like how fast we're going to rotate. And this summation is iterating through the entire signal at that rotational speed, and kind of seeing what that center of mass is going to be for a particular rotational speed, or like those multiples of it. Does that all like make sense? Okay, cool. I did try to make it intuitive. All right, so luckily we're not implementing any of that. So MATLAB already has it, Octave has it, FFT, you run it on the signal, it'll give you back the FFT, which is just a fast Fourier transform. So computers, there's certain, like when you do a DFT, there's certain symmetries that happen, especially if you do it in matrix math. And so computers just take advantage of some of those symmetries so that they can reduce the number of calculations. So they implement it as FFT, but it is basically just getting you a DFT. And so, yeah, two things. One, the signals can and should be normalized with respect to the number of samples. So you have, I mean, every time that we're kind of hitting this with, you know, kind of a rotational term, we're multiplying. This is kind of how I think about it. We're multiplying that magnitude, the overall summation. And so we're getting these repeated signals kind of overlapping. So however many samples you take for your DFT, just divide by the number of samples, and that'll kind of normalize the magnitude. And then the other thing is we looked at DFT on the real axis, but there's also, you could do that weighting vertically on the complex axis. So the actual DFT, it produces a complex value that has a real part and an imaginary part. And so you have to take the magnitude of the whole thing to make sure that you're actually looking at the whole magnitude. So yeah, that's pretty much it as far as like theory and stuff. So where this is kind of going is that we can take this DFT once we have it, and we can be given some tones and detect what tone is actually being input. It's not a super easy project kind of idea to implement. So, and there are like one or two things that need to be kind of explained. So we'll look at it next week. Today, we're just going to kind of look at the DFT function, but I did want to, we'll see how this goes. But I wanted to try seeing if I can show you kind of what the application is. When did I take this one? So this will kind of let you see like what the application is. Let me know, there should be sound that comes through from this, and it might be kind of loud, so maybe turn down your speakers. But yeah, so basically the idea is like when you're calling on like a landline especially, it does like all the different tones for whatever number you're dialing, and each number kind of sounds a little bit different. The way that those are working is that there's two tones that are at different frequencies, and so if you kind of cross-reference those frequencies and you see which two frequencies are playing, you can represent what number on the phone is actually being pressed. So it'll be like a low frequency at 500 hertz and then a high frequency at like 1100. And like that combination means that you're pressing, let's say, a 2 or something. So when you listen to it, it's really difficult to, well, to kind of understand what you're hearing. But there were people actually like back in the day who could imitate the sounds of these things, and so they could actually like trick computers into dialing different numbers and stuff. It's kind of cool. So anyway, I'll just run this because this is kind of a thing that we did to analyze what tone is being played in like a long sequence. So
I didn't hear anything. I don't know about anyone else.
Yeah, I didn't hear that either.
I'm gonna try this again. Did that come through or no? Yeah.
Yeah, that did.
So
I did, yeah.
you can't really easily tell what is you know what note is being played or anything. You can see it on this spectrogram, and this kind of shows this is the time axis, and then this is the frequency. But there's all this content here, and you can pick it out, and you could be like, oh, okay, there's like a sub 1K, and then there's like 1.4, and so you could look at that and figure it out, certainly. But what's interesting is this DFT method is actually pretty resilient. So here, if we do, we'll do a noisy one. So I'm going to cut it off there. But the idea is, I mean, if you look at this spectrogram, it's really difficult to pick out what the actual notes are that are being played. And so you can see it's running down here, and it's like actually picking out what tone is being played, and it looks pretty consistent. And that's because it is, because yeah, it does stuff. But
Is there a quick question about the
program,
domain for this?
Okay.
Sorry, I got a quick question about the domain.
Yeah.
For, I guess, like for these phone signals, none of the individual digits seem to be pure tones. Is there a reason they chose to go with kind of chorded frequencies to represent a single number?
You mean like having two frequencies?
Yeah. So like a 0 was some combination of, you know, a 0.9 kilohertz, 1.5, 3, something like that.
Yeah. There is here. We're going off. I didn't expect this, but let's see.
Sorry.
What is it? What's that company? Adafruit?
Yeah.
Yeah.
Oh, are those the matrix lines? Okay.
So of course they don't show it, but matrix.
They did it to make the hardware easier, effectively.
Yeah. So basically, you have each of these columns is kind of wired to a specific voltage, and then each of these rows is wired to a specific voltage.
Yeah.
And
Okay.
so if you press like 9, you're going to get a specific column voltage and a specific row voltage. And so it just kind of makes it, that's how they implemented it. And I guess that's just, it's easier to play just the 2 signs that correspond to whatever row and column voltage, as opposed to like combining them and having the phone have to do all of that work to figure out
Gotcha.
what resulting frequency it should be. Yeah. So anyway, yeah, so this is kind of like it builds up, but it gets to be pretty good. It's pretty useful. And so if you have this sequence, the DFT, where that comes in, is kind of looking at this. You can see it's outputting now on the bottom what note it thought. And these are actually the tones that are being played. Is like, they don't sync up to the audio exactly, but there's 2 peaks that you basically get. And then wherever you get those peaks, you can kind of tell what note is being played. And you can see that even though this is really noisy, these peaks are really well defined. So it's pretty resilient against noise. Even if you have some noise in your signal, you usually can pick out what note is actually being played, just because the noise is distributed across the entire frequency spectrum, whereas your magnitude is going to be pretty pure and a lot stronger. So yeah, very useful to be able to, you know, take an FFT and look at it. So let me switch my mic back so I can stop holding this. Sweet. So I guess, are there any questions? All right, then that is kind of it for today, in terms of like what we're kind of covering. But if you understood it all, then fantastic, because that means we're pretty well set for moving into, you know, the next steps and actually doing useful stuff and cool stuff with signal processing.